Well, hey everyone, we're back here and we're looking at the last part of section 5.5. This is linearization, sensitivity, and differentials. Today we're going to concentrate on the differentials part of this, and here we go with differentials. So we have Gottfried Wilhelm Leibniz. You can see his dates. And he's a prominent German polymath and probably one of the most important logicians, mathematicians, and natural philosophers of the Enlightenment. And of course, he, along with Isaac Newton, are often referred to as the fathers of calculus. His study of the infinitesimal is what led to much of what we're doing in calculus, and the notation that we use, dy dx, is actually the Leibniz notation. Consistently favored over f prime. It gives you a little bit more information than just saying f prime. Although the expression dy dx is written as a quotient, we have thus far used it as a single quantity. However, if you recall that dy dx was defined as an infinitesimal change in y divided by an infinitesimal change in x, then it makes sense to treat that as a quotient. So we can see over here we've got dy dx equal to f prime of x. And then if we treat that as a quotient, we can actually multiply both sides over here by dx, separating the dy dx. And what that says is that an infinitesimal change in y is equal to the derivative multiplied by an infinitesimal change in x. Of course, we can't really deal with an infinitesimal change in x, so what we will tend to do is say that the change in y is going to be equal to the derivative of x multiplied by a change in x. Now, delta x is a change in x, dx is also a change in x, but the delta x is a little bit bigger, maybe a lot bit bigger than the dx. So that's what we're saying here. We can approximate the infinitesimal change in y by substituting f for f prime and delta x, where delta x is not an infinitesimal change in x. So let's see what we have for us today. We have a spherical weather balloon with a diameter of 6 feet, and we're supposed to estimate the change in the volume of the balloon if the diameter is increased by 0.1 feet. Okay, so we're interested in an increase in volume, so it makes sense to start with the volume formula for a sphere, 1/3 pi r cubed. So the problem is in terms of diameter. What is the current radius? And that current radius is 3. And what is the change in radius? Now remember that we are increasing the diameter by 0.1. So that means we're increasing the radius by 0.05. This is a good place to mention that when we use change, a positive change means an increase and a negative change means a decrease. So we are increasing the radius by 0.05 feet. Now, we're going to find the derivative dv dr, and then we're just going to solve for dv. So if we have v equals 1/3 pi r cubed, then dv dt is going to be equal to that pi r squared. 3 times 1/3 is 1, and then decrease the power on r to the second power. And then we're going to multiply the differential dr on both sides, and that gives us that dv is going to be equal to pi r squared multiplied by dr. So that's not a big deal, a very minimal amount of mathematics involved in getting there. So now that we've done that, we're going to substitute our value of r, and we're going to use the delta r to estimate dr. So what does that mean? It means we're substituting 3 for r, because that's the current radius, And we're substituting 0.05 for dr because that's our delta r. Remember our delta r from up here that we identified. And that gets us to 0.45 pi. So if we increase, if the radius is currently 3 feet, and we increase the radius by 0.05 feet, that means that the volume is going to change by approximately 0.45 multiplied by pi cubic feet. All right, so we can estimate that change in volume very nicely just by using our derivative formulas. So here's another of the same kind of a thing. We've got the altitude in feet of a projectile t seconds after the launch is given by h equals negative 16t squared plus 10t plus 6. This is that uniform acceleration formula. I think that's what we're calling it. This is acceleration, or half of the acceleration due to gravity in feet per second squared. Positive 10 means that our initial velocity is 10 in the upwards direction. And this is our initial position plus 6. That means that our starting altitude when t equals 0 is going to be 6. Use the height of the projectile 0.5 seconds after launch and delta t equals 0.01 to estimate the change in height at t equals 0.5 seconds. Let's begin by looking at our height formula. So of course the height is as given, negative 16t squared plus 10t plus 6. Next, we're going to take the derivative because we are interested in the change in height. Change in height, of course, that should signal you to take a derivative of the height formula. Okay, the height formula derivative is negative 32t plus 10. Not a big deal so far. Let's multiply that dt, this dt, over to both sides. And now we're going to estimate the infinitesimal change in t, dt, with a small change in t, delta t. The consequence of this is instead of having an equality, now we're going to change this to an inequality because we have that delta t there. Substituting our quantities, we'll get that the change in h is going to be negative 32 multiplied by 0.5 plus 10, the whole thing multiplied over here by 0.01, which is our delta t, as we see in the formula. And that tells us that dh, the infinitesimal change in the height, is going to be approximately negative 0.06. Now remember what we said. If the differential is negative, or if the derivative is negative, that's our signal that we're having a decrease. So the height is going to decrease by about 0.06. Summarize. After 0.5 seconds, the projectile's height decreases by about 0.06 feet for every increase of 0.1 seconds. That's our problem. That's kind of how we're going to see these. Hopefully you're seeing this is not really that big of a deal. Not a lot of mathematics involved. And finally, we're going to use this in Newton's method. So Newton's method, what the heck is that? Well, Newton's method uses tangent lines to approximate the root of a function. Now the key step here is going to be setting the tangent line equation equal to 0, which is a definition of a root. So the tangent line is equal to 0. Let me rephrase that. When the function is approximately equal to the tangent line, so when the tangent line is equal to 0, the function is also going to be equal to 0. Which, when the function is equal to 0, that's the definition of the root. So like a lot of formulas, we're going to need an initial guess to figure this out. So let's start off with a given we start by looking at this, which is our regular old tangent line equation. And then we also have y naught equals f of x naught. That is our initial condition. Now, just to clean things up a little bit, that means our tangent line is going to be equal to f of x naught, which is the y coordinate, plus f prime of x naught. F prime of x naught, of course, is the derivative evaluated at f of x, at x naught, multiplied by x minus x naught. So this is actually a very familiar formula. It will look super familiar, especially when we're in second semester of Calculus BC. Next thing we're going to do is we're going to set the root equal to 0. Okay, so we have y here. We're going to make that equal to 0. And then we're going to solve here for x1. So this x1, if we do some solving, it looks like we've got to subtract x naught. And then we got to divide everything. We have to subtract f of x naught. We have to divide everything by f prime of x naught. And then we're going to have to add x naught to both sides. Algebraically, that will give us this formula right here. x1 is going to be equal to f of x naught, x naught minus f of x naught over f prime of x naught. So, two things. Firstly, since the y coordinate yn is just equal to the function, you can just substitute the function into here. Let me highlight that. You can just substitute the function right into here, and then the derivative right into there, and then you get a really nice streamlined function, an algorithm. And then number two, and maybe the most important thing here, is if you then reseed your new value, you can even get a better approximation of the root. So that's really interesting. In practice, we're just going to keep on reseeding until we have something where our accuracy level doesn't change. So let's see. Let's use this. We're going to use 4 iterations of Newton's method to approximate this function, x cubed plus x plus 1. Where is the root? And we're going to start off at x naught equals 1. So first thing in the algorithm that we're going to do is solve for f prime. So what is f prime? Well, that's just 3x squared plus 1. The next thing we're going to do is we're going to take our formula here, okay, which is the same formula that you see up here, and we're going to substitute values in. Now we know that f of x is x cubed plus x plus 1. That's this right here. So that's what we're going to substitute down over there. The next thing that we know is that f prime of x is equal to x cubed plus 1. So in the denominator here, guess what we're going to put? 3x squared plus 1. Now we're using xn because that's going to say the previous one. Now that's our formula then. So for iteration 1, we're going to substitute -1 into our formula. So here we go with our formula. We have x1 is going to be x naught multiplied by this formula with all the x naughts subbed into it. Every time we see an x naught, we're going to substitute -1. So here's an x naught, substitute a -1. Here's an x naught, substitute a -1. Here's another one, substitute a -1. Here's the last one, substitute a -1. And when you evaluate that, you'll get a better approximation of the root. You're going to get 3 over 4, -3 over 4. So what are we going to do? We're going to take that -3 over 4 and we're going to put it right back into the formula, negative 0.75. So now this was x1, so now we're trying to find x2. And every time we see an x1, we're going to be putting negative 0.75. So here, we'll put a negative 0.75. Here, here, and down at the denominator, one more negative 0.75. And when we evaluate all of that, we're going to get negative 59 over 86. Woo! That's not just, that is that decimal approximation, negative 68604. So notice with our two approximations, the ones digit doesn't change. So we're accurate at the ones digit, but the 10th digit changed from a 7 to a 6. So we're not accurate at the 10th place yet. Let's see if we get accurate in the 10th place by doing our next iteration. So x2 is this number. So we're going from x1 now. We're going to seed x2 into our formula. So x2 is negative 0.68604. And every time we have an x in our Newton's formula for this particular equation, we're going to put a negative 0.686. Now, I only use the first three digits here in the worksheet, but in your calculator, you definitely want to use as many digits as possible to calculate. And once we calculate that, we'll get negative 0.6823. So let's see which digits are the same. It looks like 0.68 is the same. And which digits are different? Well, starting with a 604, and this one's 233. So we know pretty accurately now that the root is going to be approximately negative 0.68. Those two digits are kind of a lock. The digits following that, we're not sure, but our best approximation for those following digits are going to be 233. And our best approximation now for the root, where does the equation equal 0? X cubed plus x plus 1 equals 0 when x is approximately equal to negative 0.68233. So that's Newton's method. Not very difficult, but it does require a little bit of calculus, just a little bit of calculus, and that will get you there with a root solving formula, root forming algorithm, really. So here's our important ideas. First of all, the differential is the dy or the dx part of the differential equation. You have two differentials that come from a derivative, an infinitesimal change in y and an infinitesimal change in x. Okay. Analysis of differentials can help us conclude how much the dependent variable will change. And that's, as far as we're concerned in calculus BC, calculus AB, that's all we're really worried about. Now, Newton's method is that iterative method, which means it's multiple steps, but all the steps are the same step. And it estimates the root of the equation using the derivative. All you need to do is take the old function, evaluate the y-coordinate, evaluate the derivative, plug those three things into the formula, and that will give you a new estimate for the 0. So, let's check our understanding. Okay, the function f of x equals x to the fourth changes value when x changes from a equals 1 to a equals 1 plus delta x, a plus delta x, which equals 1 plus 0.01. So if you're paying attention calculus-wise, mathematically that is, you'll notice here that without telling you, we've told you that a is 1, But furthermore, we've told you that delta x is 0.01. Those little details are the things that we're hoping to be hoping that you're paying attention to. So part A, let's find the true change of f. So delta f is f of a plus delta x minus f of a. So this is purely substitute things in. This is f of 1 plus 0.01 minus f of 1, which is 1.01 to the fourth power minus 1 to the fourth power. And that gives us 0.0406. Now for part B, let's find the estimated change. So the estimated change is this f prime evaluated at a multiplied by delta x. So f prime would be 3x cubed evaluated at 1 because a is 1 multiplied by 0.01. And that gives me and that's going to be 0.046 minus 0.01, which is 0.0306. So that's our section 5. Now I forgot. I think we're 5.5 day 2. 5.5 day 2. Newton's method is certainly a fun thing to work on. And what I like about Newton's method is it really is a computer algorithm in disguise as mathematics. So you might want to think about, if you're a computer science person, how would you create a program that would do Newton's method for you? So that's your extra assignment there. So we'll see you next time. Have a good day and good luck on your homework.